In today's lesson, we shall be looking at how best we can use the method of change of variables to solve a first order linear PDE with variable coefficients. If you could remember in our previous lesson, we learned about how we can use the change of variable method to solve a first order linear PDE with constant coefficients. So we're moving on to the second part, which is what with variable coefficients. With variable coefficients. If you haven't yet subscribed to the channel, kindly hit on the subscribe button for me. So with variable coefficient, then it means that we'll be looking at a PDE of this form. Let's say xux plus yuy is equal to, let's say, 2. So you can see that the coefficient of ux and uy are variables. Are what? Variables. So how do we solve a PDE of this form using the change of variable approach? So in doing that, we are going to use this step to serve as a guide to enable us to solve a PDE of this form using the change of variable approach. With the change of variable, as we said, we are going to change the variables from x and then y to zaya and then eta. We are going to change the variables from x and y towards a new variable called the zaya and then eta. That's what the change of variable. So let's look at these steps that is going to help us. So the first step says that identify the coefficient of ux and then uy. So looking at this equation, the coefficient of ux is what? X, and then the coefficient of uy is what? Y. So you identify it. So you can say that our a is equal to x, and then our b is equal to what? Y. Now once you identify your coefficient of ux and then uy, you form the characteristics equation. And we've already talked about the characteristics equation. So the characteristics equation is given as dx over a equals to dy over b, and then we have du all over f. So we are going to use this to form the characteristics equation. So once we form that, we solve for the characteristics variable, and then we set the solution to zero. So once we form the characteristics equation, we are going to make use of the first set of two, the first two. So we have our dx all over a is equal to dy all over what b, and then we have du all over f. So what we are going to make use of what we are going to make use of this to find the solution for the characteristics variable. And then once we find the solution, we set the solution to what? Zaya, which is a function of what? X. Very, very easy. That is what the third step says. Solve for the characteristics variable, and then you set the solution to Zaya. So once you are done or you find the solution, you set it to what? Zaya. Because the solution will be equal to what? A constant. And this constant is equal to what? Zaya, which is a function of what? X and y. And then once you are done, you choose a second variable. Since we have Zaya, then we choose a second variable called the eta. And then we set it to either x or y. So if you have to set it to either x or y, you can say that eta is equal to x or eta is equal to y. Then we find an expression for us and then uy. Then we substitute it into the equation that was given. So the equation that was given is this. You find us, you plug it into the equation that was given. And then the seventh step says that simplify and then you integrate. So once you are done with everything, you return the original variables from what? Zaya and then eta to x and y, because we change the variable from x and y to Zaya and eta. So after everything, we have to return our original variables back, which is what? Our x and then y. So these are the very few steps that we have. You can write them down and then it will guide you along. So let's look at our first example. I want to find the general solution of this first order linear PDE with variable coefficient using the change of variable. So we are going to use the step to guide us. So the first step is to identify the coefficient of ux and then uy. So from the question, our a, which is the coefficient of ux, is y, and then our b, which is the coefficient of uy, is 1, and then our f is the function on the right hand side, which is u. So once you are done, you form the characteristics equation. So we know that the characteristics equation is given as dx all over a is equal to dy all over b is equal to du all over f. So we are going to form it. So we have dx all over a, our a is y, is equal to what? Dy all over b, our b is 1, and then we have du all over our f is u. So once we have this, what we are going to use is the first two. We are going to make use of all the first two. So we are going to use it to solve for the characteristics variable. Okay, so we have dx all over y is equal to dy all over what? 1. From here, we can separate the variable into x and then y. Dx is equal to y dy. Now, since we have separated the variable from here, we can go straight away and then what? We integrate. So we have the integral of that and the integral of that. When we integrate the x, we are going to get what? X, and then we add our constant of integration, and then when we integrate y with respect to y, we get what? Y squared all over what? 2. So from here, our c is equal to what? Y squared all over 2 minus what? X. So let's clear the fractions by multiplying through by what? 2. So we have 2c is equal to y squared minus what? 2x. So we know that a constant times a constant will still give us a constant. 2 times 4 will give us what? 8. 8 is a constant. So we can write 2c as what? C. So you can write it as c, and then we have y squared minus what? 2x. So once we are there, we said that we solve for the characteristic variable, and then we set the solution to what? Zaya. So we are going to set this solution to what? Zaya instead of what? C. Because we know that c is equal to a function of x and then y, and then this a function of x and then y is also equal to what? Zaya. So we can say that our Zaya is equal to what? C. So we have Zaya, which is in terms of x and then y, is equal to y squared minus what? 2x. Since we have our Zaya, we move on to our eta. So that is the fourth step. Choose a second variable, say eta, and then set it to either x or y. So if we are to set it to x, we have eta is equal to x and then eta is equal to y. So we are going to choose our second variable, which is what? Eta, and this eta is also in terms of x and then y. So we are going to set it to either x or y. So let's set it to x. If we set it to y, we are going to get the same thing. Okay, good. So let's choose x. So once we have this, what we are going to do is to take the partial derivative of this Zaya with respect to y and then with respect to what? X. Then we take eta, the partial derivative of eta with respect to what? X and then y. So we have Zaya x. So we are going to differentiate this function with respect to x. Any function of y becomes a constant, and whenever we differentiate a constant, we get what? 0. So it means the whole of this will give us 0, and this is going to give us what? Minus 2. Very, very easy. And then we have Zaya y. We are going to differentiate the same Zaya with respect to what? Y. Any function of x becomes a constant. So this will give us 0, and then we have what? 2y. Then we move on to what? Eta x. So we have eta. Let me use it writing. Eta x. So we are going to differentiate this with respect to x. So this is going to give us 1. and then we differentiate eta with respect to y. We have what 0. So once we have this, what again? Find an expression for ux and then uy. So we know that ux, the partial derivative with respect to x, is given as u xia x plus u eta x. And then our uy is also given as u xia y plus u eta y. So this is the expression for ux and then uy. So we are just going to plug in the x in place of wherever we see the x and then the y, eta x and then eta y. So let's continue from this side. So we have our ux is equal to the x. So this is the x. We are going to have minus 2 u xia, and then we have plus eta x. This is eta x. When we substitute, we are going to get what u eta. So we are done ux, then we find uy. So uy too, we have u xia y. So this is xia y. We are going to have 2y u xia plus u eta y. So this is eta y. That is 0. 0 times the whole of this will give us 0. So you only have this. So once you have this, the next step says that substitute it into the equation that was given. So we are going to substitute it into this equation. So the equation that was given is yux plus uy is equal to u. So it means that wherever we see ux, we plug in the whole of this. Wherever we see uy, we plug in the whole of that. So we are going to have y and then ux minus 2 u xia plus u eta. Then we have uy. Uy is equal to 2y u xia is equal to u. So let's expand the bracket. This is going to give us minus 2y u xia plus y u eta plus 2y u xia is equal to u. So from here, you can see that some of the terms can cancel. You can see that this is going to cancel this. We are left with what? Yu eta is equal to what? U. So at this well point, we are going to make sure that all the independent variables in the equation are what? Either xia and then eta. You don't want to see any independent variables such as x and y in the general solution. So it means that wherever we see y or x, we change it to either xia or eta. We have y here, so we have to change it to either xia or the eta. So where do we get our y? Our y is here. So we know that xia is equal to y squared minus 2x. We want to make y the subject, right? So we can have xia plus 2x is equal to y squared. So when we take the square root on either side, we are going to have our y is equal to the square root of xia plus what? 2x. We said that we don't want to see any x or y in the general solution, so we have to change this x to either xia or eta. And we know that eta is equal to x, so it means that we can replace eta here. So we have our y is equal to root of xia plus what? 2 eta. So it means that wherever we see y in this solution, we are going to plug in what? This, the whole of this. So we have the square root of xia plus 2 eta, and then we have u eta is equal to what? U. So from here, we can separate the variables. So we are going to have our u eta all over u is equal to what? 1 all over xia plus what? 2 eta. Very, very interesting. So from here, we know that when you have ux, you can write it as del u del x. So if you have u eta, you can also write it as what del u del eta. So you are going to write u eta as what in this notation. So you are going to have 1 over u del u del eta is equal to 1 all over root of xi plus 2 eta. So from here we can separate the variables into u and then what eta. So we are going to have 1 over u del u is equal to 1 all over root of xi plus 2 eta, and then we have what the eta. Very, very easy and then simple. We can rewrite this as del u all over u is equal to 1 all over root of. Since we have separated the variables, we can just go straight away and then integrate. So we are going to integrate both sides. So when we integrate the u over u, we have a function and a derivative. So this is going to give us what? Ln u, because we can write this as integral of 1 over u del u. So we have a function and derivative, and that's going to give us what? Ln u. Very, very easy. So what about this? The integral of 1 over root of xi plus 2 eta. So at this point, we are going to make use of the u substitution, u sub. If you could remember your calculus 2, u substitution. So it means that we are going to, let's work it here, let's work it here. We are going to let u be equal to root of xi plus 2 eta. That's the u sub. So from here, we can do away with the radical sign by squaring both sides of the equation. So we are going to have u squared is equal to what? Xi plus what? 2 eta. So let's differentiate both sides. So we have 2u del eta is equal to, when we differentiate the whole of this with respect to eta, we are going to get 0. But this is going to give us what? 2. We are differentiating 2 eta with respect to what? Eta. We are going to get what? 2. So from here, we have 2u del u is equal to 2 del eta. So from here, you can see that these two cancel these two. So we have u del u is equal to what? Del eta. This means that whenever we see del eta, we can plug in what? U del u. And then wherever we see root of xi plus 2 eta, we can plug in what? U. So we are going to have integral of 1 all over what? U multiplying, we said the eta is the same as what? U del u. So from here, you can see that this u cancel this u. We are left with what? The integral of del u. When we integrate del u, we are going to get what? U. Very, very easy and then simple. So we are going to have u, and we know that our u is equal to what? Root of xi plus what? 2 eta. So it means that the integral of the whole of this is given as of root of xi plus 2 eta. So we have then plus our constant of integration. Since we are integrating with respect to eta, any function of xi becomes a constant. But realize that we have a ln on u, so we can decide to take the ln on the constant as well. So we have ln of a function of what? Xi. So from here, let's bring this to the left hand side so that we have ln u minus ln a function of xi is equal to what? Root of xi plus 2 eta. Applying our basic knowledge in logarithm Since we have len and len, they are subtracting, we can divide their argument. So we pick one of the len, we divide their argument. So from here, let's take the e on either side of the equation so that we can do away with the len and that. So you can see that the e will cancel the len, and then we are left with what? U all over a function of what? Xi is equal to e exponent root of xi plus 2 eta. So it means that this general solution is in terms of what? Xi and then eta. So we have a function of xi. So these are general solutions. These are general solutions. But realize that it is in terms of what? Xi and then eta. So the last step says that return the original variables back because the original variables were in terms of x and then y, and then we change it to xi and then eta. So we have to bring it back. We have to return the original variables back. How do we return them back? So we know that our xi was given as y squared minus 2x, and then we set eta to what? We set it to what? X. So it means that wherever we see eta in the general solution, we are going to plug in x, and then wherever we see xi, we are going to plug in the whole of that. Very, very easy. So we have our general solution, which will be in terms of x, and then y is equal to a function of our xi is what? Y squared minus 2x multiplying e exponent root of our xi is what? Y squared minus 2x, and then we have plus 2 eta. Our eta is what? X. So from here we can do some small simplification, right? These 2x will cancel the negative 2x. We are left with what? Root of y squared. And this square will cancel the radical sign. We are left with what? E exponent y. So let's rewrite it well. We have our u at x, y is equal to a function of y squared minus 2x, and then we have e exponent y, and this becomes our general solution. Very, very easy and then simple. Let's look at one more example. We want to find the general solution of this first order linear PDE using the chain of variables. So we will be applying the same concept, the same approach, the same steps like the one that we did earlier on. So we are first going to identify our coefficient of ux and then uy. So from here we can see that coefficient of ux a is what? X, and then the coefficient of uy is what? Minus y. Now once we have this, we just form our characteristics equation, and we know that the characteristics equation is given as dx all over a is equal to dy all over b is equal to what? Du all over what? F. Since we'll be making use of the dx and then dy, let's plug in the a and then the b into the characteristics equation, that is the x and the y, dy. So we have our dx, our x, our a is what? X is equal to dy all over b. Our b is what? Minus y. Very, very. So looking at this, you can see that we have already separated the variables, and therefore we can integrate straight away. So we are going to have the integral of this, the integral of that, and then the integral of that. So when we integrate the x over x, we are getting what? Ln of what? X. Because we can write this as the integral of 1 over x, and then we have the x. A function and the derivative, and whenever we take the integral of a function and the derivative, it gives us what? Ln of that function. So we have ln x, and then we have is equal to, when we integrate dy all over negative y, so we can factor the negative out, we'll be left with 1 over what? Y dy. The same thing, a function and a derivative, and it gives us what? Ln of that function. Then we have our constant of integration. Since we haven't ln, let's take the ln on the constant as well, so that we can clear the lns from the equation. We are interested in making the c the subject so that we can set it to z. So let's bring this to the left hand side. We have ln of x, then we have plus ln y is equal to ln what? C. Applying our basic knowledge in logarithm, since we have ln and then they are adding, we can do what? We can pick one of the ln and then we multiply their argument. So we have ln xy is equal to ln c. As I said, we are interested in making c the subject, not ln c. So let's take the e on either side to do away with the lens. So you can see this u cancel the ln, this u cancel the ln. We are left with what? Let me do the cancellation. So we are left with xy. Xy is equal to what? C. And as we said, we are going to set the constant c to z, because c is equal to the function of x and y, and this function of x and y is also equal to z, which is also a function of y. So from here we can say that our c is equal to what? Z. So we have z, which is a function of x, and then y is equal to what? Xy. So simply we can say that our z is equal to what? Xy. Very, very simple. Very simple. Since we've been able to identify our z, let's choose the second variable. Okay, we are going to choose a second variable, which is definitely going to be the eta. Then we set the eta. We set the eta to what? We set the eta to either x or y. You can choose x, you can choose y. Any one of them is going to work. The first example, we choose what? X. With this one, let's choose y, so that you can see that it is not always x, but you can choose what? Y. Now, once we have this, we find the partial derivative of this function with respect to x and then with respect to y. So we have x. When we differentiate this function with respect to x, we are going to get what? Y. Because y becomes a constant, and then when we differentiate x with respect to x, we get 1. 1 times y will give us what? Y. Then we take the derivative with respect to y. We are differentiating this with respect to y. Any function of what? X becomes a constant, so you can bring the constant out, and then we differentiate y with respect to y. That gives us 1, and that is what? X. So we have x. Now, once we have this, let's move on to the eta as well. We are going to differentiate eta with respect to x, and that's going to give us 0. And then eta with respect to y, when we differentiate y with respect to y, we get 1. Since there is no x, we are going to write what? 0. That is why eta x is equal to 0. Now, once we have this, we plug it into the expression for ux and then uy. So we know that our ux is equal to u xi x plus u eta x. Then we write our expression for uy. We know that uy is given as u xi Zaya y plus u eta what? Y. Very, very easy and then simple. Once we have this, we are just going to plug in Zaya x, Zaya y, eta x, and then eta y into the equation. We simplify and then we integrate. We are still following the steps. So let's start with ux. Let me use this for ux. So with the ux, we have Zaya x. So this is Zaya x. So we have y times what u Zaya. So we have y times what u Zaya. Then we have plus. Then we also have u eta x. Eta x is 0. So 0 times u eta will give us 0. So we are left with only this. Then move on to u y. So with the u y, we have u Zaya y. Our Zaya y is what? X. So we have x times u Zaya. X times u Zaya. Then we have plus u eta y. Eta y is 1. 1 times u eta, we have what? U eta. Now once we have this, the next step is that substitute ux and then uy into the equation that was given. So the equation that was given is this. We are going to plug in these two expressions into this. Wherever we see ux, we plug in the whole of this. Wherever we see uy, we plug in the whole of this. We simplify, we integrate. So we have the equation is so our ux is what? Yu Zaya. Then we have minus our uy. This is uy. So we have x u Zaya plus what? U eta plus u is equal to 2. So from here we can expand the bracket, right? So this is going to give us x, y, u Zaya. And then this time this we are going to have minus x, y, u Zaya. This time this is going to give us minus y, u eta plus u is equal to 2. So you can see that some of the terms can cancel, right? You can see that the whole of this will cancel the whole of that. We are left with what? Minus y, u eta plus u is equal to 2. Very, very interesting. So at this very point, we don't want to see any independent variable x and then y in this equation because we are dealing with what? The Zaya and the eta. So it means that wherever we see y, we make sure that we plug in either Zaya or eta, and then wherever we see x, and so on. So you know that y is given as what? Y is given as eta. So it means that wherever we see y in this equation here, we can plug in what? Eta. So here we are going to write it as minus eta u eta plus u is equal to 2. Very, very easy and then simple. So what do you think we are going to do here? What do you think we should do here? Or from here, what do you think we should do? We want to integrate. We want to find the solution at this point. Now let's divide both sides of the equation by negative eta and then let's see something. So we are going to have u eta. This will cancel this. Then we have minus u all over what? Eta. And then we have is equal to what? Minus 2 all over what? Eta. So from here, you can see that this particular equation resembles a certain type of differential equation which is of the form dy all over dx plus p of x y is equal to what? Q at x. So you can see that we have the function
and e derivative here. We have the function and then a derivative. So with this one too, we have the function u and its partial derivative. Now from here, if we are to match it, you can see that this will correspond to that, this will correspond to that, and then this will correspond to that. And whenever you have a differential equation of this well form, you make use of the method called integrating factor. So we are going to make use of the integrating factor to help us solve this differential equation. Let's continue from this side. So from here, our p at x is equal to the coefficient of u, and that is going to give us -1 all over what? Eta. You can see that we are no longer dealing with x and y, but rather z and then eta. So our p at x is going to be what? P at eta. Eta. So we have p at eta, and then our q of x is what? This one, that is -2 all over what? Eta, and we are dealing with what? Z and eta. So this q at x will become q at eta. Very, very easy and then simple. Now once we have this, we find our integrating factor. So we know that the integrating factor is given us. So we have the integrating factor is equal to e integral of p at x dx. And as I said, we are using what z and eta for independent variables. U is equal to e integral of p at eta the what? Eta, because we are dealing with what? Z and then eta, not x and y. So when we plug in this, we are going to have e exponent integral p the eta is for -1 over eta, then we have the eta. So we have our integrating factor, which is going to be e. So when we integrate, we can bring the negative out. We have 1 over eta, the eta. So from here, you can see that we have a function in the derivative, and that's going to give us ln. So we have negative ln what? Eta. Now you can decide to bring the negative on top, so that you have this. Applying some of our laws of logarithm, you can write it as that. So from here, we are going to have our ln, and then we have raised to the power -1. So from here, you can see that the e will cancel the ln, and then we are left with what? This is eta. So we have eta raised to the power -1, which is the same as 1 over what? Eta. So our integrating factor is 1 over what? Eta. Now once you know your integrating factor, we find our general solution for the integrating factor. So we know that the general solution is given as the integral of q at x. We know that q at x is what? Q at eta. So we have q at eta multiplying the integrating factor, and then we have what? The eta plus a function. Since we are integrating with respect to what? Eta, any function of z become a constant. So we have a function of what? Z all over what? The integrating factor. Some of you are getting confused. Now the integrating factor is giving us y is equal to the integral of q at x multiplying the integrating factor, and then we have what? Dx plus what? A constant all over the integrating factor. So this is what the integrating factor. But realize that we are no longer dealing with x and then y. We are dealing with what? Z and then eta. So with the x we have z. So with the x we have eta. So wherever we see x, we plug in what? Eta. Then the constant, since we are differentiating with respect to eta, any function of z becomes a constant, and that is why we are having this. Very, very easy. So we have u at z eta is equal to q at eta. We have negative integral of -2 all over eta multiplying the integrating factor, which is what, 1 all over eta, and then we have what, del eta plus a function of what, xi all over 1 over what, eta. So let's do the integration first. So we have the integral of u xi eta is equal to, so we have the integral of, we can factor the negative 2 out, we are left with, this is going to give us 1 all over n squared del eta. This is the rate. So we can write this as negative 2 integral of eta raised to the power negative 2 del eta. Now applying our basic knowledge in integration, we are going to have negative 2 plus 1, then we have negative 2 plus 1. So this is going to give us negative eta raised to the power negative 1. And this is the same as negative 1 all over what, eta. So when we integrate the whole of this, we are going to get what, negative eta. So we have negative 2 and then we have negative 1 eta. This is going to give us what, 2 all over what, eta, and again 4. So we have 2 all over eta plus a function of xi all over the integrating factor 1 over eta. So we have u xi eta is equal to, so we can write this as 2 all over eta multiplying eta over 1 plus a function of xi all over what, 1 all over eta. So from here you can see that this eta will cancel this eta. We have our u at xi eta is equal to 2 plus, we can also write this as eta multiplying a function of what, xi, because we can write this as xi times what, eta all over 1, and that's going to give us what, eta multiplying a function of what, xi. So this will have been our general solution. U at xi eta is equal to this. But I realized that the question was given in terms of x and y, right? So we have to return our original variables back. Our original variables are x and y. So that is the last step among the steps. Return our original variables back. So it means that we have to find the expression for xi and then eta. So we said that our xi is equal to what, xy. And then we set the eta to what, y. So it means that wherever we see eta, we are going to plug in y. Wherever we see xi, we plug in xy. So our general solution is now going to be x and y, not xi eta, is equal to 2 plus eta, we have y, and then we have a function of what, xi equals xy. Very, very easy and then simple. So this becomes our general solution. This brings us to the end of today's lesson. See you tomorrow. Bye bye.